I'm a teacher at the Center for Advanced Technical Studies in Chapin, where I teach some pre-engineering classes. And in those classes, my students are exposed to lots of physics principles, lots of math principles, and they're actually expected to be able to go and solve some real-world problems. Last year, I stumbled across a technique in which I was able to show students how they can actually map out word problems and come up with a graphical organizer to allow them to solve it. But before I get into that technique, what I'd like to do is take you on a journey and show you sort of how I arrived there. Recently, I moved, okay, and in the process of moving, I came across my high school report card during my senior year, and it had a guidance counselor interview on it. And the interview stated that I said that I like to make things work, I like to make machines run, and it was recommended that I should pursue engineering in my college career. Okay, that was in 1977. So that's what I did. Okay, I went to Rutgers University, where I majored as a mechanical engineer, and one of my favorite thoughts or favorite memories in that was in an Introduction to Computing for Engineers class. Okay, where basically I was taught to do some programming, and the cool thing was I was able to make the computer work. I was able to make it do the things I wanted. What I also remembered was that I liked helping my colleagues, my fellow students, with their particular problems. I would hang around the computer lab. And it even crossed my mind back then that I could probably do this. I could teach these concepts to high school students. Where did that thought come from? I pushed it out of my head. Turns out college was not without problems for me. Okay? Every class had word problems in it. And for me, they were not the easiest thing. As a matter of fact, I felt sort of like I was either blind or I was walking around in a forest going around in circles. Okay? I eventually got better at this by my senior year. I did like college, however. I liked it so much that I hung around for a PhD, which was paid for through a teaching assistantship. And I was teaching the Introduction to Computing class for engineers. Now, in that process, one of the questions that came to my mind was, how do people actually learn? After graduating, okay, I worked as an engineer, as a project manager, an engineering manager, and basically consultant, helping other people make things happen. And then in 2002, a change took place. I decided I was going to become a high school teacher. 23 years after having had the thought in an engineering computer lab, okay, I was actually going to go for that. The question of how people learn was going to get its due in my teacher training. One of the things that I learned, okay, was that there's actually two kinds of learning, or there's two major kinds of learning. The most difficult learning is where somebody basically has never been exposed to it before. They have nothing to build on. The easiest learning is where there's already a framework of knowledge that exists, and the concepts can be hung on that particular framework. The technique I'm about to show you falls into that category. Solving problems has often been described like solving a puzzle. You have to make the pieces fit together. But what are the pieces, and how do they fit together? Well, if we look at solving a puzzle, the first thing that we have is you look for the corner pieces. They're easy. There's only 4 of them. They have corners on them. And next, you look for the side pieces. They have the straight edges, and they connect the corners. And then finally, you fill in the middle of the puzzle by looking at how the images matches and the shape matches for everything that you've already put down. Okay, well, it turns out that this is exactly the same technique that you use when you're actually solving a math word problem. Okay? What are those pieces? The pieces turn out to be the physics principles, the math concepts that have been given, such as area, perimeter, things like that. The corner pieces represent your givens and your finds. What information do we have, and where are we going? What's our objective? The edge pieces are those that fit directly to the corner pieces. You look for a relationship that directly connects with your given, and you look for another relationship that looks for whatever you're trying to find, and you hook those up. Your centerpieces are finding all the connections in the middle. Okay, we're going to look at an example problem. I'm glad that the previous speaker gave some math before this. Given a perimeter of 18 feet and a length of 5 feet for an enclosed rectangular space, determine the area and width for the space. Now, for this particular problem, the scope of knowledge we need are basically the perimeter relationship and the area relationship. Now, it turns out for this technique, the actual formulas are almost irrelevant. The only thing that's important here is that perimeter has 3 variables, P, L, and W, and area has 3 variables, A, L, and W. And those are the things we actually have to know to be able to solve the problem. Okay, let's lay out our corner pieces. Okay, our first piece, the given, is we've been given a perimeter and a length. So we make that piece of the puzzle. And then we make the other corner, which is what is it that we're trying to find? Well, we've been told we need to determine the area and the width for this particular problem. So those 2 pieces have been laid out. The next thing is, where can we find our edge pieces? Okay, well, the edge pieces, our perimeter relationship, that hooks up very nicely to our givens. We were given a perimeter and a length. It has 3 variables. We can connect those 2. And if we look at our find, we're being requested to find an area, so there is an area equation we can use, so we put that over here. Now, here's the thing. For this particular technique, in which you're solving problems with direct substitution, there's a little rule with these pieces. You have one output on the right-hand side, you can find an answer, and you have to find whatever the other variables are. If those are given, you can go ahead and get an answer. So if we take a look, our perimeter, we have 2 inputs we can find width. Somebody will have to do the algebra, but we know we can do it. The middle of our problem is now we make all these connections. Okay, 2 inputs on perimeter says we can find the width. But our area required width and length. So we can take the width that we found and connect it over. And the length was one of our givens. So we can bring that over. And if we look at our find, we see width. Well, that was solved back at the perimeter equation. So we connect that. So with these cards and pieces of yarn, you can see I've made all the connections. Okay, some mathematicians would say the problem's actually already over. I can prove I can solve it. Well, it turns out that if you actually do want to solve the problem, you really have to do the math, and this is where the math comes in. We now know the math we have to do. The perimeter equation has to be expressed to find width. We can substitute values that have been given to find a width of 4. Using the found width and the known length, we can substitute that into the area and come up with our area, and now we found our answers. Okay, so the steps have been figured out. Now, in this previous example, what I did is I used cards and pieces of yarn. There are people who like to use physical approaches, but some people are happy with just drawing pictures. So in this case, here's an example of a different problem in which you just graphically draw it out to be able to go and work this out. Turns out this technique not only helps you solve word problems, but it also provides a foundation for some very real engineering skills. In the upper right-hand corner, I've got an example of a LabVIEW program. LabVIEW, you actually write real-life programs by connecting boxes with lines to pass data through it. In the lower left-hand corner, I have something called breadboarding, in which you physically connect electrical components with wires to make an active circuit. The technique I've shown provides a foundation for this. I hope you found this talk useful. If you'd like more information and like to see how these techniques could actually be applied in Excel or LabVIEW, you can go to the website tinycc/wordproblem. Thank you.